Let's understand collisions in this video. Have you seen two billiard balls hit and scatter? Or a car hitting a spring bumper at the garage? Collisions are short events where bodies push each other hard for a very short time and their speeds change suddenly. In these events, momentum and sometimes kinetic energy move between bodies or into other forms like heat. A collision has three stages: before, during, and after the hit. Before the collision, bodies move normally and are far apart. During the collision, strong short forces act, and after the collision, the bodies move apart or together under ordinary forces. In an isolated system, the total linear momentum stays the same during the collision. That is, momentum is conserved. Kinetic energy is conserved only in elastic collisions, while in inelastic collisions, some kinetic energy changes to heat or internal energy. Collisions are classified as elastic or inelastic by energy and as one-dimensional or two-dimensional by geometry. Let us look at an example to make this clear. Question number 1 asks, one sphere collides inelastically with another sphere of the same mass at rest, and the coefficient of restitution equals 1 divided by 2. Find the ratio of their speeds after collision. Call the masses m1 equals m2 equals m. Initial velocities u1 equals u and u2 equals 0, and final speeds v1 and v2. Conservation of momentum gives u equals v1 plus v2 because m cancels out. The restitution relation says v2 minus v1 equals e times u, and here e equals 1 divided by 2, so v2 minus v1 equals 1 divided by 2 times u. Now add the two equations. v2 plus v2 equals 3 divided by 2 times u, so 2 times v2 equals 3 divided by 2 times u. Thus v2 equals 3 divided by 4 times u, and v1 equals u minus v2 equals 1 divided by 4 times u. So the ratio v1 to v2 is 1 to 3. So the correct answer is 1 to 3. Next example. Question number 2 asks about a particle of mass 0.15 kilogram moving with speed v that sticks to a block of mass 2 kilogram and compresses a spring by 0.1 meter. Find v. Use conservation of momentum first. 0.15 times v equals 2.15 times capital V, where capital V is the speed of the combined mass after collision. Thus, capital V equals 0.15 divided by 2.15 times V, which is about 0.0698 times V. Then the combined kinetic energy becomes spring potential. So 1/2 times 2.15 times capital V squared equals 1/2 times 250 times 0.1 squared. Solving gives capital V squared equals 2.5 divided by 2.15. So capital V is about 1.08 meters per second. Now back substitute to find V equals 2.15 divided by 0.15 times capital V, which gives V about 15.4 meters per second. So 15 meters per second is the closest option. Example 3 is an assertion reason type about kinetic energy conservation during contact and energy lost to friction. Both statements are incorrect because kinetic energy need not be instant by instant conserved during contact, and conservation of energy always holds as energy simply changes form. Finally, a two-dimensional example. Three equal masses move along medians of an equilateral triangle towards the center with equal speed v. After collision, A stops and B reverses with v. Find C. Momentum was 0 before, so after collision, total momentum must remain 0. Resolving horizontal and vertical components and solving gives C moves with speed v in the direction of B. So what do we learn from this? Momentum is always conserved in isolated collisions. Kinetic energy is conserved only in elastic cases, and the restitution relation links relative speeds. Let us quickly remember. Divide problems into momentum equation and energy or restitution equation, and solve the simple linear system for unknown speeds. Keep practicing one-dimensional and two-dimensional cases separately, draw clear diagrams, and write component equations. Thanks for watching. Take a calm step ahead in your practice and explore more worked examples on EduRev to build confidence.